The gravitational pull of the moon creates two huge water tidal bulges on the surface of the Earth. The massive sun also causes ocean tides, but its impact is significantly weaker than the lunar one. During syzygy, the effects of the moon and the sun combine, forming a maximum spring tide. The friction of the huge tidal wave gradually slows down the Earth's rotation, increasing the total length of a day.
Welcome! Today we will conduct a rigorous examination of the physics that govern our oceanic tides. It's a phenomenon many of us observe, but the science behind it is, well, it's far more elegant and complex than a simple gravitational pull. So let's begin with the central paradox of the tides. Common intuition might suggest that the moon's gravity should pull the oceans into a single bulge, resulting in one high tide per day. Yet, as our observations confirm, we experience two. This discrepancy is our starting point, and it signals a much deeper physical principle at work. Our analysis today will proceed through 5 sections. We'll start with the fundamental force responsible for tides, then we'll examine the mechanism that creates the tidal bulges. After that, we'll incorporate the sun's influence, compare our theory to the complexities of the real world, and finally, consider the profound long-term consequences of this entire process. So first, we must isolate the fundamental concept. The cause of tides is not gravity per se, but something more subtle. It's a differential force. The key concept is what we call the perturbing or tidal force. You see, the moon's gravitational pull is not uniform across the Earth. It pulls more strongly on the side of Earth nearest to it and less strongly on the side farthest away. This difference in the gravitational force across Earth's diameter is the actual driver of the tides. Now imagine for a moment that the Earth was an unyielding, perfectly rigid sphere. This differential force would still exist, of course, but it would be absorbed internally, manifesting only as immense mechanical stress within the planet's structure. There would be no visible external effect. However, Earth is not rigid. It's covered in fluid oceans and a fluid atmosphere, both of which are free to move. And it's the response of these fluids to the perturbing force, their deformation and flow, that generates the phenomenon we call tides. All right, let's move on to the mechanism. How does this differential force produce not one, but two tidal bulges? To understand this, we'll employ an idealized model. Let's picture a simplified Earth, perfectly spherical and covered by an ocean of uniform depth. We'll define 3 points of interest. Point A, on the surface nearest the moon, also known as the zenith, point T, at the very center of the Earth, and point B, on the surface farthest from the moon, the nadir. As expected from the inverse square law, the moon's gravitational acceleration is strongest at the nearest point A, weaker at the center T, and weakest at the farthest point B. These vectors visually represent that gradient in gravitational pull across our planet. Now here's the crucial step. We must consider these forces relative to the acceleration of the Earth's center, T. At point A, the water is pulled toward the moon more strongly than the Earth's center is. The relative acceleration is therefore directed away from the Earth, creating a bulge. At point B, the Earth's center is pulled toward the moon more strongly than the water is. The effect is that the Earth is pulled away from the water, leaving the water to form a second bulge on the far side. And there you have it, 2 opposing tidal bulges. Let's look at the mathematics for a moment. The crucial term in this approximation is at the bottom, r cubed. This shows that the tidal force is inversely proportional to the cube of the distance, not the square like gravity itself. This makes the tidal force extraordinarily sensitive to distance, a fact that will become critical when we introduce the sun. So the net effect is a distortion. Gravity is effectively weakened at the zenith and nadir, allowing water to rise. Along the perpendicular circle, gravity is actually strengthened, squeezing the water. The result is that the ocean flows towards points A and B, deforming from a sphere into an ellipsoid with 2 bulges. Of course, Earth does not exist in a simple two-body system. We must now account for the influence of the sun. As the Earth rotates, a point on its surface passes through both of these tidal bulges. However, the moon is also orbiting the Earth in the same direction. This means the Earth must rotate a little extra each day to catch up to the moon's new position. This defines the lunar day, which is approximately 24 hours and 52 minutes, the true period of our 2 high and 2 low tides. Now for the sun. While it is vastly more massive than the moon, it is also immensely farther away. And because of that inverse cube relationship we just discussed, distance dominates. The result, as this chart illustrates, is that the sun's tidal force is only about 46% that of the moon's. The moon is, without question, the primary driver of Earth's tides. Consequently, the sun's effect is to modulate the lunar tides. When the sun, Earth, and moon are aligned, a configuration known as syzygy, their tidal forces combine constructively. This produces the maximal tides, or spring tides. When they form a right angle, a configuration called quadrature, their forces act against each other, resulting in the minimal neap tides. Let us now transition from our idealized water-covered sphere to the much more complex reality of our own planet.
In reality, our simple ellipsoidal model is disrupted by several factors. The continents act as massive barriers, preventing the tidal bulges from propagating freely. The complex shapes and varying depths of ocean basins channel and alter the flow. And we must also account for friction with the seabed and the sheer inertia of the water itself.
These factors introduce a significant delay. High tides at a given location does not coincide with the moon's transit overhead. This lag, known as the applied hour, is a direct consequence of real-world geography and friction, and it varies from place to place.
This leads to extreme variations in tidal amplitude. While the tide in the open ocean might be only a meter and just a few centimeters in enclosed seas like the Black Sea, the unique geometry of basins like Canada's Bay of Fundy can create a resonance effect, resulting in staggering tidal heights of up to 18 meters.
Finally, we'll consider the cumulative, long-term effects of these tidal forces on the entire Earth-Moon system.
The constant friction of the tidal bulges dragging against the rotating Earth's crust acts as a brake. This initiates a chain of consequences. First, Earth's rotation is gradually slowed, increasing the length of our day. Then, due to the conservation of angular momentum within the Earth-Moon system, this lost rotational energy is transferred to the Moon's orbit.
The most direct and measurable consequence of this energy transfer is that the Moon is spiraling away from the Earth. Its orbital distance is increasing at a rate of approximately 3.8 centimeters per year.
This leaves us with a final thought to contemplate. In the distant future, this process will continue until Earth's rotation slows to match the Moon's orbital period. At that point, our planet will be tidally locked, presenting the same face to the Moon at all times. A day and a month will become one and the same, and the rhythm of the tides as we know it will cease.
Thank you, friends. Strive for understanding and become wiser. See you soon.